Berkeley to give us the final talk of this workshop. And Professor Salahuddin introduced the concept of using interacting system for ultra-low energy switches, leading to the idea of the negative capacitance transistors, and with a number of awards. So let's welcome Professor Salahuddin.
So let me start by thanking the organizers for inviting me here. This has been a fantastic symposium from my perspective, and it's my first time in Hong Kong, so thanks for giving me that opportunity. So if you notice that today's speakers are all somehow connected to Intel. They're either currently at Intel or were previously at Intel. So I thought that I changed the first slide. I thought that I should not start with Moore's law because I should try to be different. So what I'll do is I'll start with Star Trek. And so this is something that a colleague of mine at Berkeley, Ali Vikneja, and I often talk about, is that we are probably, we can consider ourselves very close to a Star Trek generation. And our motivation, rather than Moore's law, could be just this. That is what is to be human, to make yourself more than you are. Captain John Wilson. And so let me try to go a little bit deeper into the motivation. And that is, I'm showing here some gadgets that we have seen in the Star Trek. Okay, so this is a flip phone. This is a universal translator. This is a touch screen. You see the massive storage. It looks very much like a USB drive. Okay, this is a tablet computer, holodeck, wristwatch, and this is a tricorder. Okay. These guys, except for the tricorder, all of these exist today. Okay, and in fact, in more efficient forms than what was shown here. Does anybody know what a tricorder does?
Yeah, doesn't it see what your biological status is and checks to see if you're okay? And
exactly. Yeah. So it scans your vitals, right? And it can scan your vitals from a distance. So we have some gadgets that are close to it, but not directly. But not of that stature yet, which probably gives us a hint what application we should work on. Okay, so in more serious sense, that these gadgets exist today independent of the Moore's law, just because A, they are very cool, and B, that they have improved the quality of human life somehow. That's what I believe. And so I believe that the fact that we will have a heavily connected, heavily integrated cyborg-like life, that is inevitable. Okay, that's going to happen, either following Moore's law or following something else. But that's going to happen. That is inevitable. So one question that we could ask is that how are we going to power all these devices? Supplying energy for all these devices is a problem, and I stole this slide from Ilya Yakunovich. It shows the power taken, energy dissipation in the data centers in 2005. So there are some new data available now, but let's just look at 2005. And if you look at in 2005, the world data centers are taking the energy consumption is comparable to a mid-sized country in the world in 2005 when we were not using iPads, tablets, and others. Of course, that has increased significantly by now. So the energy consumption is going to be an extremely important problem, and that is a main point of my talk. I'm going to talk about some materials that may help us to make electronics more energy efficient. I'm an academician, so I look at not so practical devices. So we have to see whether they can actually find an application, but they at least show us what is possible. So this is a tentative outline of my talk. It will go, we will see how it goes. So the first is, I'm going to talk about 3 different material systems which I'll try to motivate that they help us do what is usually considered impossible. And the second part is some non-technical random thoughts. So we will see how we do about this. So again, our motivation is taken from Star Trek, right? So things are impossible until they're not. So the 3 different material systems that I'm going to talk about are ferroelectric materials, 2-dimensional semiconductors, and ferromagnets. Okay? So let's start with a ferroelectric material. And what I'm going to show, hopefully, very briefly, is that a ferroelectric material, by exploiting the stored energy in that material, it may be possible to do something like an electrostatic transformer, something like a device that can boost up a voltage from one node to that internal node. And if this is a MOSFET channel, and if I can boost the supply voltage at this channel node, then my IDVG, rather than looking like this black curve, could look like the red curve, because I'm actually increasing the electrostatic voltage right on the channel. And that can help us reduce, what we call the subthreshold swing, but just from this curve, that can help us get to the current level that we want at a smaller voltage. So that can help us reduce energy dissipation. Question is, how is that possible? So it is possible if I have something called a negative differential capacitance. So what we know from textbooks is that if we put 2 capacitors in series, the total capacitance will go down, and the voltage at the internal node will be a divider. It will be determined by the capacitance division of these 2 capacitors. But let's imagine, we will see how it can be possible. Let's imagine that this C1 is negative. Okay, so dq dV is negative. Your large signal capacitance is still positive, but dq dV is negative. If that is the case, I just use this 1 over C equals to 1 over C1 plus 1 over C2. If C1 is negative, you can see that the total capacitance will actually go up. And if the total capacitance in the network will go up, and at the middle node, you see the total voltage will be V minus Q divided by C. But C is now negative, so the internal node voltage will be larger than supply voltage. Okay? We are not doing any energy amplification. It's just a voltage amplification. It is like a transformer. Okay, so from your primary to secondary, the energy remains the same. It's just the voltage is going up. All right. So, question is, how is that possible? How can ferroelectric help us do that? So, what I'm showing here is the energy landscape of a ferroelectric material. So, this is energy versus Q, and we know that it needs to be something like an even function of charge, because we know a ferroelectric material will give me a hysteresis. Hysteresis means that in either direction I go from this zero electric field, I can find the same state. So therefore, here and here I have 2 degenerate states, which means that I can have this kind of a symmetric hysteresis. Okay? So if I now look at this energy landscape, you see that I can compare that with the energy landscape of a regular insulator. Okay? And the energy landscape of a regular insulator is given by Q square over twice C, just a parabola. So you see that here and here, it is just like a parabola. I could have fitted a parabola at these 2 places where the energy is minimized. But here, where the energy is not minimized, the parabola has a reverse sign. It is an inverted parabola. So if I'm trying to fit a Q square over twice C, the C needs to be negative. Okay? So I'm just making a hand-waving argument, but you can just go through the math and you will find it to be negative, simply because the parabola is inverted. So the thing is, if I can actually create a situation that the ferroelectric, rather than sitting in this minimum energy position, rather than sitting there, it sits here, it will give me a negative differential capacitance, except the problem is this is not the minimum energy position, so if I put it here, it will try to fall down. So it is exactly like what Suman was talking about in negative differential resistance. By itself, it is not stable. You can push it there, but it will come out. So you need a stabilization. And we know in negative differential resistance devices, you can put a series resistance and stabilize it. So in this negative differential capacitance device, I can basically put a series capacitance and stabilize it. And again, just from an energy idea, you can understand the stabilization. You see that if I have this thing, the black curve, which is for the ferroelectric, and this blue curve, which is for a regular capacitor, the resultant energy landscape will look like this red curve. I'm just adding blue and black. And so if the slopes are properly matched, the red will just look like a regular capacitor, except for its curvature has gone down. And the curvature is going down basically means that your capacitance has gone up. Because again, I can fit another q squared over twice c here. So if to get the same charge, I need smaller energy, c must be larger. Okay? This also tells us how I'm going to reduce the supply voltage, because this basically is showing that in this capacitor, I can get the same charge at a smaller voltage, smaller energy. So how is this relevant for a MOSFET? In a very simple sense, I can, again, look at the MOSFET just like an electrostatic device. Electrostatic is 70% of the device, almost. So I can say that this is my gate insulator, this is my semiconductor insulator, this involves all the source drain capacitances, everything. This is a series capacitance network. If I can create a negative differential capacitance here, the voltage here will go up. So as a result, if for a conventional case, conventional MOSFET, I was getting this, now I will be getting that, because the voltage here is larger than VG. So that's the idea, that if I can put a ferroelectric material on top of a MOSFET channel, use it as a gate insulator, and be able to stabilize it right there, right at the point where it is negative, it gives me negative differential capacitance, I can basically reduce the supply voltage. Now, more mathematically, I can look at this equation, which basically tells us how does the drain current change as a function of gate voltage, which is defined as like this and called subthreshold swing, right? And many, Suman has talked about it, and Mark has talked about it, that there is a limit for 60 millivolt per decade. And this can be seen from here. I can write this thing as a product of two terms. The first term is del Vg del psi s, where psi s is a node voltage. So this is just the capacitor divider formula. It is saying that how much voltage, the inverse of how much voltage I get here if I put certain voltage there. And because in a conventional capacitor network, your internal node voltage is always smaller than the supply voltage, this factor is always larger than 1. The second one is a transport one. It is saying that if I change this barrier by a certain amount, how much current would I get? And the electrons at the source is arranged by the Fermi function. So if I change it, I get an exponential current. So that gives me that 60 millivolt per decade. So in a tunnel FET, what people are trying to do is to change this part, this transport part. What people are saying that let's not go over the barrier, rather let's go through the barrier. And that way, we can basically avoid going through the Boltzmann tape. Now, what we are saying that let's work on the first term. Can we create a situation where the electrostatics become such that this factor gets less than 1? The good thing about this is then I do not have to really worry about the trade-offs that Suman was talking about, that how much on current can I get? Because I'm not changing the transport of the MOSFET. I should get as much on current as a normal MOSFET gives me with a smaller subthreshold swing. Okay? So, with that, let's kind of try to summarize what I have talked about. So I said that if I can put a ferroelectric material and stabilize it in the negative differential capacitance, then I'm going to get a voltage amplification at the internal node. It's an electrostatic voltage amplification, very difficult to measure. But we can measure it by seeing that the total capacitance of this network has gone up. Okay? So again, as an academician, I want to look at that system. I want to put two capacitors in series and see if the capacitance can go up or not. Okay? So we will show some experimental results on that, but before that, let me talk about the ferroelectric material a little bit, which will help us to understand the experimental results. So in a ferroelectric material, if I look at the relative permittivity as a function of temperature, I see this kind of behavior. So right at T equals to Tc, the permittivity goes to, quote unquote infinity. In a physical material, it won't go to infinity, but it will go to a very high value. So what is happening? So we start with this W shape, this double well shape. I'm increasing temperature. I go here. I get this blue curve. Okay, I increase temperature even more. At some point, the energy landscape just becomes like a regular dielectric. At that point, we say that the phase transition has happened and ferroelectric has become a dielectric material. So it is, usually it is governed by this Landau's mean field theory, which basically says that the energy is an even function of the polarization. So everything is symmetric with respect to plus P and minus P. That's all. And this first parameter, is proportional to T minus Tc. So when your temperature is less than T, you are in the negative, your alpha is negative. When you go above the Curie temperature, alpha becomes positive. And you can see that the capacitance, from those of you who are more mathematically bent, for capacitance I have to take two derivatives of this function. So what I get is basically alpha. So if alpha is negative, I get a negative differential capacitance. If alpha is positive, I get a positive differential capacitance. So therefore, in the ferroelectric phase, I should expect to get a negative differential capacitance. In the dielectric phase, I should not. So that's the idea. But the reason that I went there is that, let's say I'm doing an experiment. I'm putting a ferroelectric material in series with a dielectric material. I want this stabilization to happen. I want it to come here so that the resultant looks like the red curve and it is exactly stabilized at the top of the hill. But if I cannot make that stabilization very well, I may find myself in this kind of a situation where the resultant look like this green curve. So say that this slope is not good enough to overcome this black slope. So I'll get a green curve like this. Now I'm outside this box where the derivative was negative, so I will not actually see a negative capacitance behavior. But what I can do is now I can increase temperature, and then I can change the resultant curve like this. I will get inside the negative capacitance zone, except that I will still have some hysteresis. Because I still have the double well, I can keep increasing temperature. At some point, the hysteresis will go away, and I'll still see the negative capacitance. So that's the idea, that we will follow to actually experimentally probe this hypothesis. So you can go through some calculations to kind of understand what kind of materials and what kind of temperatures that we should need. And it is a very simple calculation. You just use ferroelectric, dielectric. You know that the potential energy for the ferroelectric will be given by this Landau's formula. For the dielectric, it is a simple dielectric equation. You basically say that I will solve Poisson's equation in this system. I say that the voltage will have to be add up. This part plus this part should give me the total voltage, and the charge will have to be the same in both materials. You use those two boundary conditions, and you can find curves like this. So what I'm plotting here is C versus V, capacitance versus voltage. So the red curve shows ferroelectric plus dielectric. That PE basically here is saying paraelectric, but it's basically a dielectric. So that heterostructure capacitance versus that paraelectric capacitance. So what I'm saying is, let's say I take a paraelectric, I measure CV theoretically, and then I put some ferroelectric on top of the paraelectric. I again measure CV. Okay, and I compare them, and I'm looking at it, and you can see that if I look at around the zero voltage, I see that the paraelectric capacitance is much larger than the heterostructure. So it means that I'm not seeing any negative capacitance. But as I'm increasing temperature, at some point, I'm going into this situation where my red curve is above the blue curve, which means the heterostructure is giving me larger capacitance. This is the negative capacitance region. But I still see some hysteresis, I keep increasing temperature, the hysteresis will go away, and I will start seeing very large non-hysteretic negative capacity. So to test this hypothesis, what we have done is we have grown these epitaxial heterostructures. Okay? So this is our control structure. This is STO, strontium titanate. It is sitting on top of strontium ruthenate, which is a metal oxide, and it is chosen because it makes it possible to epitaxially grow STO. Okay? And to compare with it, what we are doing is we are putting a PZT on top. This is our ferroelectric. So remember, I want to emphasize on that point that if I have a material and then I put another material on top of it, the thickness has gone up. So according to standard theory, my capacitance should always go down because the thickness has gone up. Okay? So let's see what happens. So these are some materials that some growth results. We basically want to boast that our materials are very good. You can see that our interfaces are extremely abrupt, and lattice, you can essentially see the atoms themselves, very nice single crystalline films. And these are grown using this pulseless deposition technique. So now these are some experimental data. Room temperature. So what we are comparing is strontium titanate dielectric material 48 nanometer, that with strontium titanate and PZT. So it is still 48 nanometer, but plus 28 nanometer extra thickness sitting on top of it. Room temperature, I find a hysteretic behavior of the heterostructure. The capacitance is much below STO. I do not see negative capacitance. Okay? I increase temperature. You see that now this 76 nanometer thick heterostructure gives me higher capacitance compared to the 48 nanometer STO. Okay? And so this means that I am seeing the negative capacitance now. But I still see hysteresis. I keep increasing temperature. At some point, the hysteresis goes away, and the amount of negative capacitance that I see also goes up. So therefore, these experiments actually show that the negative capacitance at least conceptually works. Okay? So again, just to compare our results with the simulation results that I showed, it kind of qualitatively follows. So we think that we kind of understand what's going on. So to kind of find out why we were having to go up so high in the temperature, we did lots of XRDs. Okay, so our calculations, initial calculations, were based on bulk PZT parameters. And what this curve is showing, the temperature versus lattice parameter. So when there is an inflection point like this, I can explain if somebody is interested. This shows the Curie temperature, because your ferroelectric material is tetragonal. You're increasing temperature, so it is coming down. It is becoming more and more cubic, and your A-axis is going up because of temperature. So at some point, this going up will take over this going down. So you will see coming down and going up again. So at the cross point, you see the Curie temperature, and this is the bulk Curie temperature. It gives you around 430 degrees centigrade. But when we grew our thin films, the epitaxial thin films, we went up to 650 degrees centigrade, but we could not see the Curie temperature. It is simply because STO compressively strains the PZT, so it becomes much more tetragonal. And as a result, we are not seeing Curie temperature even up to 630 degrees centigrade. This is just 50 degrees below our growth temperature, so we cannot go above this because our LEDs will all go away, the whole lattice will change. So therefore, what this says is that because of that compressive strain, the parameters that we are using our simulations are way off. And so we have to actually increase the temperature artificially in our heterostructure to get to this negative capacitance region. So we have done, after we understood this, we did lots of studies and looking at materials and what could give us a good negative capacitance at room temperature. So I'm not going to all those details, but this is just a result. So what we did is we decided to grow this super lattice rather than just bilayer. We said, let's grow BSTO LAO. Okay, it's a very strange choice of materials if you are tuned to this literature. because BSTO and LAO have almost a 5% lattice mismatch. It's extremely difficult to grow them epitaxially. But we wanted to do that anyways because people know how to grow LAO on silicon. On the other hand, epitaxially. On the other hand, BSTO, I can change the stoichiometry and change its Curie temperature. So this is why we chose to do this, and took us almost a year to stabilize the phase so that we can grow a superlattice. But when we were able to grow this, we saw this negative capacitance effect at room temperature. So what this is showing is capacitance of the constituent LAO and capacitance of the superlattice as a function of frequency, and you can see that the superlattice actually has a larger capacitance compared to the constituent LAO. So this again shows that the whole, at least conceptually, the negative capacitance effect works. Okay, and so therefore it is possible to reduce the subthreshold swing in a MOSFET below 60 millivolt per decade using this effect, and without giving up the transport time. That's the idea. Now, one thing I wanted to point out, and Suman actually pointed out this very well for VO2 systems. If you think about it, this is actually a controlled phase transition. That is what we are trying to do. Because again, if you look at the energy of the ferroelectric, this up to the third term, this is what the ferroelectric has. Once we are putting a standard capacitor in series with it, I'm increasing the energy by P square over twice C, where C is the capacitance of that capacitor that I put. So now, you see that I can take these two P square terms together. So what is happening is this alpha is going up by 1 over twice C. Remember, in the ferroelectric phase, alpha was negative. So I'm actually making it less negative. What that means is, let's say my isolated ferroelectric had a Curie temperature around, let's say, 300 degrees centigrade. By putting the dielectric capacitance in series, I am actually pushing the effective Curie temperature towards a lower temperature. And so therefore, if I can be in this region, in this hatch region, my permittivity will be extremely high. And you can now start to bring in all this positive feedback mechanism that is there. That is actually part of the Landau-Green field theory anyways. So therefore, that is a controlled phase transition that we want to do, and this is why the materials problem becomes extremely difficult, because materials do not want to be controlled like this. They will break into domains, they will give all kinds of issues, and all these complex material systems are very difficult to integrate with silicon. So we have been working for almost 2 years to make a MOSFET. And we, I keep telling Suman that just last month, after 2 years of work, we have gotten our first 3-terminal results. Forget about good transistors. It's just the integration is so difficult, at least in a university environment. But there has been some demonstrations of negative capacitance transistors already. So in 2010, this group from EPFL, Adrian Ionescu's group, what they did, they were much more savvy than us. They said, let's not talk about single crystalline ferroelectrics. Let's just put a polymer ferroelectric and see what we see. It's not a practical device because polymer ferroelectrics cannot be switched beyond a few kilohertz. But they wanted to see the effect. They put a polymer ferroelectric, and yes, they were seeing 50 millivolt, 46 millivolt per decade at various points of their IDBG. Okay, but it was not a very, very clean experiment. There are some certain things that we can point to, but it was a preliminary demonstration. So this year at IBM, Intel came up with a very interesting result where they showed that in a nitride-based system, by putting nitride, so this indium gallium nitride as a piezoelectric gate material, they're seeing less than 60 millivolt per decade. Again, it's not very clear exactly why this is happening, but it has some signature of negative capacitance effect. So why is that? You see that if you look at this device, when you have this aluminum indium nitride, which is this layer, when you do not have that layer, the dashed curve shows the CV. Okay? When you have that layer, the solid curve shows the CV, and you see that the capacitance after increasing the thickness of your gate dielectric is actually higher. So that is mathematically again gives you a negative differential capacitance in this region. And it's an Intel's experiment, so the data is very clear. There is no noise related issue that we can see here. But the jury is out as to the exact mechanism of this. But at least in its behavior, it looks like a negative capacitance effect. I mean, quote unquote negative capacitance. So where are we currently? So I showed that we have shown. I should also mention that there were 2 more experimental papers in this year's IEDM showing this negative capacitance effect. Again, these are not extremely convincing demonstrations, but there are interesting effects in each of those papers. So we can talk about that. So it looks like that people are starting to get some results in the transistor range. So what I have shown is that in my group we were able to do these capacitors, where we showed that you put 2 capacitors in series and the total capacitance goes up rather than going down. But we were initially able to just do it at a high temperature. Now we can do it at room temperature. So that's an improvement. People are starting to see some negative capacitance effect in transistors. And this is one of our collaborators and one of Suman's collaborators too. This is a work with MBE grown STO coupled with silicon. So this gives us some kind of a template to grow our complex oxides on silicon, which is a very difficult work otherwise. Now, one question that always comes up is, hey, we know that ferroelectrics are slow, so how fast can you switch? Now, the thing is, actually, it looks like, from theoretical point of view, the ferroelectrics are not that slow because we are not looking to switch them from one side to the other. We are only trying to modulate them. And Suman talked about how much charge density we get at the inversion layer of the MOSFET. 10 raised to 12. A ferroelectric, the saturation polarization, the materials that we grow are 10 raised to 14 per centimeter square. So we are only talking about 1% of the polarization modulation. So therefore, we are not going to strain that unit cell extremely, strain that unit cell as much as we will do in an FEDAM, for example. So there are all these things, and then there is these experimental results that people have done in electrical switching of ferroelectric, where they see 10 to 30 picosecond range of switching. That's a full switching of the polarization. So, again, we have to see in a MOSFET how fast can we switch them, but they are not very slow. They're not like kilohertz systems. So this is where I'll end the discussion of negative capacitance. I'll go to the second system now, but I want you to kind of appreciate why we think that the negative capacitance devices are going to give us low power MOSFETs. Okay, so the next material system is 2-dimensional materials, semiconductors, and so our journey with 2-dimensional material systems started with this paper. This came out at toward the end of 2010, and when I saw this paper, I immediately told my students who were heavily frustrated with caffeine, if you are an experimentalist, you can do all kinds of things and publish papers, but if you are a modeling person and you do one modeling and you see that it doesn't make sense to do either digital or analog with caffeine, then you are heavily frustrated. So my students were at that point. And then we saw this and we said, yes, we found a 2-dimensional materials with band gap and we should all go there. Except that we did not know other people were already working with it. So even before we could finish our calculations, Andras Kies's group actually published a paper on transistors. So, that was a very interesting time when we were all looking at it. We are not connected. Andras is a Berkeley alumni. So I knew him, but I did not know that he was actually looking at it. But we were all looking at this material system, and this is a very interesting material system. You see that it's a layered material, so you can get one monolayer. It gives you something around 2 volt band gap at the monolayer case. It has a very high effective mass 0.5, so it can give you large density states, which look pretty good initially. So. At Berkeley, in my group, we have our own NEGF simulator. So again, not too much to talk about. We have these NEGF equations. We have Poisson's equations. We solve them self-consistently. and and we look at various device behavior. And this is a scaling behavior. This is, we usually show it, especially to experimentalists. So this show that we see ideal scaling up to 8,000 processors, 8,000 cores. But I can show you ideal scaling up to 150,000 cores. That's what we have done, and it parallelizes very well. Except for the fact that those of you who do simulations, you know that these are all what we call the embarrassingly parallel simulations. So these are all energy and transverse modes are all independent. So as long as you take care of your job distribution well, it parallelizes. There is not too much to, there is not too much credited. But if you get access to that kind of 150,000 cores, you can do large problems very fast. So that's it. And in our group, we are calling our simulator Synapta. Simulator for nanoscale transport. We think that it's a better name than Nemo. But anyways, I mean, you can see that it is very difficult for someone to say that Synapta is bad, right? Synapta is not bad. So, all right. But anyway, so we did these first pass calculations in 2011. The question that we asked is, how good can monolayer MOS2 transistors be? This is an effective mass based ballistic calculation. Okay? Except for the fact that we took care of the contact resistances and others from Andras Pieces published experiments, and he was very generous to send us some even data so that we can calibrate the contact resistance from there. What we found was not very good. Okay? The reason is, you see that if you look at, this is ballistic current, if you look at the amount of current I'm getting with a sweep of almost 1.2 volt, this is around 2 milliampere per micron. Okay, it's a pretty large current, except for the fact that this dope here is extremely slow. That once you go here and it bends back, that bending back is very slow. What I mean by that is, when I plot ion versus ion I-off, if I choose 10⁵ right here, I do not even hit a few hundred micron per micron. That's the problem. Okay? And at this point, we realize that this is coming because of the effective mass. Because the effective mass is very high, we get a lot of charge, except for the fact that a low effective mass material gives you the same kind of current at a smaller voltage. The total on current may still be smaller, but by the time you reach the very high on current ranges, you actually have to put very large voltages across.
So in terms of the ballistic velocity, just to put into perspective, 1/10 or 1/20 of silicon?
Not 1/10, but something like 3 times 1/3 or something like that. That's what we extracted out of this. So we kind of stopped this paper. We kind of concluded this paper in a pessimistic form. We kind of said that maybe this is good for low power electronics because you can get very large on-off ratios because of the very high band gap, but probably not good enough for high performance electronics. Okay, but to some extent this was expected. The reason we went there is because I can get these monolayers which gives me extremely good gate control and very large band gaps, so the leakage current will be very small. But what we also wanted to get is a very high on current, which we do not get. Okay? So, but anyways, this field had picked up since then. Many people are working on various aspects of it. So recently this year, we wanted to do another study where we said, let's look at a very small channel length device, let's say 5 nanometers. Okay? And now, what we will do is we looked at the band gap. We said that we will confine ourselves within a 0.5 volt voltage sweep, and we can see that the band-to-band tunneling current can be completely ignored because it's a 2 volt band gap material. If I'm putting 0.5 volt, I can completely ignore it. So we want to see how much source length tunneling current I get at a 5 nanometer channel length. And then the second question we asked is that can we boost up the amount of current we get by increasing the number of layers from one monolayer. So the thing is, if I increase the number of layers, I'm losing gate control. But there may be a trade-off. So I'm losing gate control at the expense of higher on current, and there may be a good trade-off. That's what we wanted to see. We also, something we did, we said that let's look at a zero Schottky barrier contact. No Schottky barrier there. So basically zero Schottky barrier is still not go. Why not? I'll come back to it later. But basically we said that let's try to put as much current as possible in this device and see what happens. So what we did is, we took this VASP and we tried to do some band structure calculation. We saw that this is very well known that if this is for MOS2, you get two degenerate valleys very close to each other in energy. And we did the similar kind of band structure calculation for all these different materials, and we fitted some effective mass from it. We did not need a full band calculation because the BTBT is not very important here. So now we look at the IDVG. Okay, so we are looking at two different voltages. For monolayer MOS2, you see that the gate control is very good, almost 60 millivolt per decade. But as I go to 5-layer MOS2, you see that gate control becomes very bad. It is no longer even close to 60 millivolt per decade. That's what we see. And that's what we see for all the materials that we have tried. So here I'm showing MOS2 and tungsten selenide. So for 1 layer, 2 layer, 3 layer, 5 layers, you see this is 1 layer, this is 5 layer. You can clearly see that the gate control is going on.
So where does the conduction happen? Is it in all the layers, or it's only a portion of the layer?
So let me come back to it. So the thing is, when we presented these results, some of the experimentalists in the room at IETM came to me after my student gave the talk and said, this is not real, because in our experiments, we see at 5 monolayers, we get 60 millivolt per decade. So my answer to them was, even we see 60 millivolt per decade with 5 monolayers in our own experiments. And so why in our simulations we are not seeing this? The reason is very simple. The thing is, all our contacts are very bad. Okay, so we cannot push as much electrons as the layers can take. So what we see is once the device turns on, the topmost layer goes to very close to what you can get for 0.5 nanometers. So it is very far away from quantum capacitance limit because of the very high density of states. As a result, it totally spills out your gate electric field. So therefore, the layers at the bottom do not even see it. So it just acts like a dielectric layer sitting there. So this is why, when I'm saying that, let's assume that my source and drain are very good, I'm putting so much charge into the system that I cannot actually go beyond 1 monolayer. Okay, and so this is the thing, that we want to increase the contact resistance, but not increase, meaning improve the contact resistance, but when we go to the limit, it looks like that, we cannot go beyond 1 monolayer. So, Professor Lundstrom showed you some of this kind of calculations for 5 nanometer silicon, for example, and he showed that you get a lot of source drain tunneling current. At for MOS2, we don't see that, and that's expected. You have a very large band gap there. So that is good. But now, again, we play that game. We want to see how much ion we get for how much ion. And you see, when I do that, this is for 10 raised to 5, right? You see, only monolayer and 2 layers can actually go there. As you go above it, they're very far from the 10 raised to 5. So the thing is, I'm not actually gaining anything by going above monolayers. And even when I have 1 monolayer, my current that I get for 10 raised to 5 is 450 microamp per micron. If you see ITRS roadmap for 5 nanometer technology, at 10 raised to 5 on off, they want 660 microamp per micron. Okay, so my ballistic current calculation is giving me less current than what ITRS wants. Now, you can take it in 2 different ways. You can say ITRS needs to change. Because you can say that silicon will not give me this, Okay, because silicon cannot give me 10 is to 5 at 5 nanometer node on-off ratio. M12 gives me 10 is to 5 on-off ratio, but does not give me the on-current. So, I know that Max Piscetti has made this similar point from just a screening length calculation. He says that you have to go to something that is extremely thin, otherwise you cannot go to the on-off ratio. But this is a problem. I mean, this basically shows that forget about high performance, right? I'm talking about low performance technology. I'm not even hitting the on-current necessary for the low performance technology. So it does not look very good. But there is one thing we realized, and that is, we do experiments too, and we try to do heterostructures, and we realize that because we can layer transfer them, and they have compensated surface, it is very easy to make heterostructures with them. Okay? But we looked at the literature and we saw that Novoselov and Geim are making heterostructures. Philip Kim is making heterostructures, and we said, okay, how do we compete with them? They are making 2D heterostructures. So one of the things that we thought that we do not have to be bound to 2D heterostructures. I can make 2D 3D heterostructures. Okay, so one of my postdocs. His PhD was on amorphous silicon electronics. He made X-ray sensors. So he said that, hey, if I look at the ionization potential of MOS2 with amorphous silicon, it looks like that I'll get an abrupt p-n junction here. Okay. Now, if you look at the the imagers that we use in X-ray imagers and others, for large area application, doping is so expensive that people don't dope it. People just use a metal semiconductor junction to collect light. So we said that, okay, now if I can create a PN junction like this just by putting an MOS2 and amorphous silicon, I can use a built-in field here to collect the light and separate the carriers. The second thing we realized is that amorphous silicon has extremely low mobility, less than 1. Now MOS2, people quote mobilities from 1,000 to 20, but it is much larger than less than 1. So if I can separate a charge out into the conduction band of MOS2, this will go much faster. So my speed of the imager will become very fast. Okay? So we tried to do a very simple experiment. The whole experiment and data taking took 1 week. It took much longer to write the papers, and even longer to publish it, and even longer, even so far, we could not actually model it. So that's one of the problems that I'll talk about. One is the modeling problem. But it's a very simple experiment. We just put amorphous silicon, we just layer transfer and MOS2 on top, and we look at the dark current and the photocurrent. And you see that dark current are the same for an amorphous silicon, just amorphous silicon photodetector, and an amorphous silicon MOS2 heterostructure photodetector. But the photocurrent is 2 orders of magnitude higher almost. For the heterostructure, I get almost 2 orders of magnitude high current, and this is what we expected because I'm creating a PN junction. Okay, so the junction increases the sensitivity. If I look at the imager speed, this is the amorphous silicon, conventional amorphous silicon imager speed. This is amorphous silicon MOS2 heterostructure photodetector, and I get a 0.25 millisecond response time, which is almost 2 orders of magnitude smaller compared to commercial photodetector. Okay, so we were actually very happy with these results. We are not from photodetector literature, so we did not know that it could be very important. After we published the paper, actually after the paper was published, we got contacted by industry because essentially what they said is that the speed of the amorphous silicon photodetectors has been stuck at a few milliseconds for almost 20 years. They cannot reduce it. And this system can actually reduce it. Okay, so, and this is a big deal because this can reduce the X-ray exposure time for a patient by a significant amount. So, again, this is something that was very interesting, very easy to do, and I think that this takes what the intrinsically what these layered semiconductors can offer us, and that is to make heterostructures without worrying about heteroepitaxy. So that's the idea. So, these are some characterization results. We just, created the same structure on a doped magnetic substrate just to measure the IGBT and look at the mobility. And the mobility gives us something around 27. Again, we are happy if we are 10 times larger than less than 1. So this works. So again, this slide summarizes the results. If I look at the photosensitivity, our heterostructure diode gives us a little bit larger sensitivity than what commercial amorphous silicon photodetectors give and what MOS2 thin film junction gives. But if you look at the response time, we are almost 2 orders of magnitude faster. Okay? So this ends my second example. Okay, so again, the idea is that what I'm showing is these unconventional materials are helping us to do things that we could not do with conventional materials, but they may not be exactly good just to replace the conventional applications. You are basically doing something a little different. So, 2D semiconductor electronics. This is my personal view, and feel free to disagree with me. Can 2D materials good for electronics? Remains to be seen. But it looks to me that it is unlikely. Okay, because it is not being able to catch even the low performance limits. And as you saw from Sumon's talk, that they are reducing the thickness of their indium arsenide layer, they are still getting mobility of 4,000. Okay, so once they're close to 2 nanometer, 2.5 nanometer range, it is very hard to actually make a case for 2D materials. Can 2D materials find a niche? Absolutely. If we can find out large area growth processes for 2D materials, there are many different heterostructures you can make, which can be very useful for very different. All right. So the last material system is ferromagnets. Okay. Now, ferromagnets are of course commercial materials, and this what I'm showing here is a memory hierarchy in a system, and we know that we know about the magnetic tapes, we know about the hard disk, but there's a big push to see if we can make embeddable non-volatile memory, which will try to take out some of these level 2 cache, or if possible even level 1 or even SRAM. But that's where the push has been. And it all started with this MRAM, which basically says that I have a pin magnet, I have a soft magnet, I put a field. Once I put a field, I can change the direction of this magnet, the soft magnet. So when they are pointing the opposite direction, I get a high resistance. When they are pointing the same direction, I get a low resistance, and I have a hysteresis, so I can use it as a magnetic memory. So MRAMs are of course commercial. This is the company Everspin, which has a product on MRAM, and you can see that their cells are increasing. So this is from them, so don't blame me for it. But the problem, of course, is if you look at the current that you need to switch the magnet, okay, for a conventional MRAM by creating a magnetic field, it goes up as you decrease your node size. So it is not compatible with scaling, and as a result, after 90 nanometer node, the MRAM scaling has stopped. Okay, so this technology does not scale, except for the fact that there is this new kid on the block, which is called a spin transfer memory, where the idea is that I put a spin polarized current so that, let's say, up spins are going from here to here, and they go through an exchange interaction with the software magnet. Because of the exchange interaction, it switches. And if it switches, I come from a high resistance state to a low resistance state. And then I can put a current from the other side and it will switch back. So now the x-axis is no longer magnetic field, but it is current. Okay? And because it is current, now the amount of current I need is proportional to the footprint of my device. So if my node size is going down, the current is going down, and this is what is shown here. For STT-RAM, the scaling goes like this. So there are some real data and there are some projections here. Okay, but this is how it is supposed to go down. And so STT-RAM, this basically shows all the big companies on the map which are trying to commercialize STT-RAM right now. So if we look into the physics a little bit, how this device was, you can see that it's mostly by generating spin current. So you can imagine that there's a spin. So this is the fixed magnet. When I put a current from top to bottom, electrons are going from bottom to up. These spins will come into this ferromagnet, soft ferromagnet. And when it is going through the soft ferromagnet, it is getting absorbed in the soft ferromagnet. So you basically see a rate of change of the spins. That gives you the spin current. So you can basically say that the spin current is absorbed by the soft ferromagnet, that switches the magnet. And that's how the spin transfer torque device works. Question is there a different way to generate a spin current? The way I'm generating it here is I am trying to inject polarized spins through here. So there is an injection efficiency, how much polarization I can get, all this stuff. Can I avoid that somehow? And one of the ideas that has been around for a long time, essentially it was predicted by Diakonov and Kendall in 1971, is this spin Hall effect. So the idea is that if I have a material system where I have the spin orbit coupling, okay, and you can imagine, let's say I have an impurity sitting somewhere. So if I put a current, okay, it will the electron will scatter. As a result, you will create an asymmetry between positive K and negative K. So if you have something that is, K cross your electric field, you will get two different types of polarization on both sides. So the physics that I described is often called the extrinsic spin Hall effect. But there is an intrinsic spin Hall effect for which, if you have an inversion symmetry breaking in the material itself, you will get this current. But what you need is a very large spin orbit coupling to see appreciable amount of up and down spins. And it was experimentally first shown by David Osholm's group in a 2D electron gas, gallium arsenide in 2004. So it is beautiful physics, but it was not very applicable because you are only accumulating spins at the two edges. And so the number of spins that you get by doing this is very small. It does not give you any appreciable effect. So the idea was that, can I change the geometry like so? And now if I push a current like this, I should get I should get spin accumulations at the top surface and at the bottom surface. And now if I put a ferromagnet on top, and if I can accumulate enough spins here, they will get absorbed by the top ferromagnet. So it is like the ferromagnet is absorbing some spin current and it may switch. So the question is, does it work? And so what I'm showing here is some of my group's work. This is a stack that we have grown. This is copper-iron boron is a ferromagnet. MgO is the oxide layer and the bottom layer is tantalum. Tantalum is a massive material, so it has a spin orbit, large spin orbit coupling coefficient. And there is also this thing that there is an inversion symmetry breaking just because of the way the structure is grown. You have tantalum at the bottom of the ferromagnet and MgO at the top. So it is not symmetric. And remember that the magnet here is just 1 nanometer thick. Okay? So what we do is, we just do an anomalous Hall effect measurement. It is simple, just the measurement wise is just a normal Hall effect. I put a current here and I measure a magnetic field from here. I measure a voltage from here. And what you can see that, yes, absolutely, I can switch the magnet back and forth by putting a current. Okay, so this is a perpendicularly polarized magnet. So to switch it, I need an in-plane magnetic field to sit there. If I had an in-plane polarized magnet, it will switch without a magnetic field. Now the interesting thing here is that, you see, unlike the STT-RAM, I'm not putting the current from top to bottom. I'm putting the current here. So therefore, the current density that I need, the spin current density that needs to be absorbed by the ferromagnet is still the same, because I have to satisfy the spin angular momentum conservation. I need to, if I'm switching 10 spins in the magnet, I need to give it 10 spins. So that spin current density is still the same, but my current density is proportional to the cross-sectional area here rather than the footprint of the ferromagnet. So I can imagine that if I, even looking at a 10 nanometer feature size, by making the thickness of the tantalum layer 1 nanometer, I can reduce the current by 10x, even at the lowest node. And initially a group from Japan, Hideo Ono's group, already showed that in a 1 nanometer tantalum, you can actually generate this kind of spin current and switch a magnet, and many other groups have reproduced it, including ours. So this works. Okay? So, so again, you see that this is a new material system. This tantalum, as a material system, it is very old, but we are using this new property of a spin angular, of a spin orbit coupling to do something that we could not do before. So last night when I was finalizing the slides, I was thinking about what I should do from here. Should I talk about memory or should I talk about something else? What to do with this. So I decided to talk about something more exotic than memory. So I'll talk about how we can use this for something we call the nanomagnetic logic. So before I go there, one thing I wanted to show is that let's look at this structure a little bit. So I have this ferromagnet perpendicularly polarized. I have a current coming in the plane. And so if I look at the ferromagnet, its easy axis is out of the plane, so it wants to be out of the plane in the in-plane direction. It does not want to remain there. So if I put a current, the spin accumulation is in the in-plane direction. It can bring it to in-plane, but it's a metastable state. If I shut off the current, it will then go randomly to up and down. Okay? So when we do a micromagnetic simulation, we basically find that when the current is on, the ferromagnet essentially breaks into some up and down domains, which is better stable. Experimentally, when we look at a 150 nanometer by 150 nanometer magnet, this is the data we see. So let's try to explain this a little bit. What we are doing is we are saturating the magnet in one direction, putting a current pulse, then going back and measuring where the magnet is. And as we do, as we keep putting pulses, we randomly find we get up and down directions. So this basically says that by putting the pulse, I can push the magnet to a metastable state. Okay? So that then helps us to do what we call the nanomagnetic logic. So the idea of a nanomagnetic logic is that I can create this dipole coupled ferromagnets. So all these magnets, due to their dipole coupling, want to be in an up-down state. Okay? Now I can put a magnetic field and push them to their hard axis. In that axis, they are metastable. Now when I put the magnetic field off, depending on which direction this input magnet is, they will either go to an up, if this was up, it will go down, up, down. Okay? Or if it was down, this will go up, down, up. Okay? So this kind of magnetic logic systems has been extensively studied. Okay, and experimentally, theoretically, and people have shown that you can do Boolean logic. These are experimental results. You can do majority gate logic. People have also shown that you can do something people call phase logic, and for pattern matching and all kinds of stuff. So there has been lots of experiments showing that in principle the logic system works, except for the fact that you have to give that magnetic field to push the magnets to a metastable state. Okay. And so when people do the experiments, they're putting their chip inside this humongous electromagnet, right? So when you're looking at, this is not a practical system. But there has been some studies where people are putting these embedded wires inside the substrate, and you put current in the embedded wires, and you create a magnetic field that way. Okay?
Can I ask a question here?
Yeah.
It's very nice the opening tracking does this transfer code. But this current does generate a magnetic field. Is that effect not very important, or you have accounted that for?
So that effect is, so I'll give you an idea. So at 150 nanometer by 150 nanometer magnet, the coercivity is, in our magnets, we get a coercivity of 300 Gauss. The amount of current we are pushing, it creates a coercive field, let's call it that Maxwellian field, of the order of around 4 to 5 Gauss. So it is there, and there are some very important physics questions to be answered, meaning because of that field, you may be breaking a time reversal symmetry which may be important to push, certain things, but it is by itself not enough to do something. So, to look at this a nanomagnetic system, logic system, where we will clock the magnets not with a magnetic field but with a spin orbital, we created this structure. So this is an input magnet, and then we have these small dots. And you can imagine that creating this 30 nanometer spacing in a university fab took us a long time, right? So, but finally we were able to do this, and using this Hall structure, we can actually see where the magnets are. And so this is the experimental data. What we see is we start from a completely up, all the magnets are put in the up direction. We put a current pulse. So this is the clock pulse. And then we find all the magnets in the 2 down, 1 up state. Okay, that's what it should do, because if this is up, second one should be down, third one should be up, fourth one should be down again. So it should be in a 2 down, 1 up state. And then we do the opposite thing. We saturate everything to down, so the input magnet is now down. We clock it. Once we clock it, it goes to a 2 up, 1 down state. And so this basically shows that we can get this nanomagnetic logic to work. We actually did statistical measurements, so we did many measurements and see how much errors we get. So if you are interested, you can look at the details in this paper. But this is the main point, that we can actually show that that nanomagnetic logic circuit works. And more importantly, this is what happens. So these 4 are the only experiments where people have created the magnetic field by embedding wires inside the substrate. These are, you can call an on-chip integrated nanomagnetic logic systems, rather than putting your chip inside a huge electromagnet. And if you're looking at the amount of current they were using and the amount of current that we are using, our current, this is an experimental current going from the source. No de-embedding has been done. But still, we are 3 orders of magnitude lower compared to the stable current.
How big are these, trying to understand, of course, we've got dipole moments, and so they interact.
Right.
That's going to limit the cell size. Otherwise, these magnets are just going to talk to each other.
Right.
All directions. So what's the pitch? Have you thought about what the minimal pitch is that should be?
So, we have not done ourselves many calculations on that, but many people have done that for, because nanomagnetic logic people have been looking at for some time. So the idea is that if you get perpendicularly polarized magnets, which are like this, then if you have a 50 nanometer diameter of the magnet, then you need around 10 nanometer spacing. For us, of course, we are working in a much more favorable range, because these are around 150 nanometer by 150 nanometer, and then we have a 30 nanometer spacing. But the people have done lots of calculations, and I know that with a magnetic field 60 nanometer by 60 nanometer magnets with a 20 nanometer spacing has been demonstrated by IBM, Stuart Hawkins.
What's the advantage of this over normal charge technology?
Okay, so that's a much harder question to answer. So the hope is that switching the magnets take less energy compared to switching a MOSFET, and there are lots of calculations theories showing.
But how much energy do you use now?
Right. So okay, I should have put that that slide in. I don't have it right now here. So we have done some calculations based on how much current we want. We are putting in here. What we see is that the energy dissipation we have so you can look at this as a 3 inverter connected one next to the other. So we are lower in energy dissipation compared to a high performance logic 3 inverter chain, but we are higher than substation logic. Okay, but our speed is extremely small. Our speed is actually comparable or smaller compared to a substation logic.
The speed is lower or the time is lower?
What do you mean? I mean, it's
better.
Oh no, so no, we are slower,
So, yeah.
somewhat slower compared to subtraction logic, but energy-wise we are much worse compared to subtraction logic. We are better than in terms of energy dissipation, high-performance logic, but of course we are much slower than high-performance logic. So that's where we are. But people make various arguments. For example, for applications like so, let's say that you are doing pattern matching. So people will say that with this kind of dipole coupled structures, you can do it much more efficiently compared to using a full digital processor. Those are more architecture level arguments, which does not it is difficult to explain with a device. So we are so the main thing in this case to show was that we are doing a magnetic logic now with the spin orbital, which has no magnetic field anywhere. Input, output, clocking, everything is electronics. And compared to what used to be the state of the art, we are 3 orders of magnitude lower in current and 5 orders of magnitude lower in energy dissipation. So before that, if you took the amount of energy you dissipate in creating the magnetic field, you would be almost 6 orders of magnitude away from subtraction logic.
What's wrong with the Russell Coburn stuff is all Russell Coburn stuff, these multi-layers and so on, those are much more costly.
Those are so far much more dissipative because he's still using a external magnet, rotating magnetic field. Yes. But I could see that he could use a similar physics to actually take that out. Sure. All right. So again, where are we? Do I have 10 minutes?
Yeah, sure.
Okay. So basically, this is the end of my technical part of the talk. Okay. So the main point that I wanted to get across is that what I tried to show is that using these unconventional materials, we have shown 3 examples where we have been able to achieve things that are otherwise kind of difficult to get with conventional materials. For example, I showed that you can put 2 capacitors in series and the total capacitance goes up. I showed that you can create these photodetectors which are 2 orders of magnitude faster than commercial ones. I showed that in a nanomagnetic logic you can reduce the dissipation by orders of magnitude, many orders of magnitude using this tantalum or platinum, or you can think about other material systems. And none of this is actually trying to replace silicon. The only thing that is trying to replace silicon is 2D materials, and from our calculations it does not look like that. It is likely that will happen. So that's the thing that I think that there may be many opportunities. How much of this can actually find its way into real applications? That remains to be seen, but it actually at least shows what is possible. So then, for the next 10 minutes, what I'll talk about is to some extent my own experience of doing exploratory device research in my group. So for those of you who do not know a lot about me, I come from Purdue. I did my PhD at Purdue with Professor Sukyodata. So my training is as a theorist. Okay, but in my group at Berkeley, only a small portion of the people now do modeling. Most of the other people are doing experiments. So I find myself in this situation that Professor Lundstrom kind of pointed to, where I have a group of people doing experiments, I have a group of people who are doing computational stuff. And how do I bridge the gap? Okay, and I was just telling Professor Lundstrom that for somebody who is doing computational part, they get very motivated by the fact that, okay, there is a software called Nemo, let's go and make a better software. They like that chase. But the problem is that there are so many problems with our own experiments that we cannot explain. So let me start with that. And I have chosen to only talk about 2D because I think more people here are working on 2D than ferroelectrics or ferromagnets. So while looking at these 2D systems in the last 2 years or so, I have come to appreciate this statement that my supervisor made many times during the 5 years I was with him. And that is that calculating and understanding are two different things. So, what I mean by that? You see that I have very boldly shown that, I look at the ionization potential of amorphous silicon and MOS2, and we believe that I should get a PN junction. We put it, we get a PN junction, everything works beautifully. But we don't know why this works. Okay? The reason is that this is supposed to be a 2D material. The only interaction with the amorphous silicon should be just van der Waals, some kind of a van der Waals interaction. So we don't know why there is a significant amount of charge transfer at the interface. Okay? And this is very critical. We have no way to basically know what kind of heterojunctions we can make because we don't know how that charge transfer happens. This is not like a 3D material where you can talk about wave function overlap between this material and this material. When I put amorphous silicon on MOS2 or vice versa, does this MOS2 essentially become in a three-dimensional material? Or what happens? How to think about it? So, Suman was pointing to making tunnel FETs with 2D materials. Very naively, that seems to be what you should never do because you are putting two 2D materials one on top of the other. All the mobility, all the good properties are in plane. Out of plane, if I do a naive DFT calculation, I see that out of plane the band structure is flat. There should not be any electron essentially going out of plane. But we have made this heterostructure. Other people are making heterostructures. They are seeing diode-like behavior. It works. So the thing is, good DFT theorists probably know the answer, but we don't know. And we don't know how to intuitively think about it. And that is very important. We need to understand how this interface will work so that we can actually design better devices. So this is, to me, very, very critical. Understanding how the charge transfer should happen in a 2D material interface. So the other observation that we have, and almost everybody who is doing experiments with these layered 2D materials have, is that I take a substrate. So this is the insulating substrate. I put a layered dichalcogenide material here. I look at the current. People usually talk in terms of mobility, but there are all kinds of extraction problems of mobility. So let's not even think about mobility. Let's say that I put a very high backgate voltage, so the current saturates, and I just look at how much current I get. Okay? I look at that current, and I look at the current by putting some high K dielectric on top. The current goes up by almost 70, 80, 100%. And this is not only us, almost everybody who does the experiment sees it. And in fact, if you look at the first transistor paper by Anders Kiss, what he's saying is that we have figured out a way of putting ALD HFO2 on MOS2, and therefore, rather than getting a mobility of less than 10, we are getting 200. I mean, it turns out that he was still getting a mobility of 10. But the idea is that the current actually goes up. Now, there are all kinds of theories that, for example, is that these layered materials have different vibrational modes and they get suppressed if you put a high K dielectric on top. I'm not sure that that is a right way to think about it because why would high K matter in that case? It's not clear. There are other questions that people say. People say that all these things have lots of defects and putting a high K suppresses long-range Coulomb interactions. And now you see that as a computational person, I have a problem because my NEGF simulator guys cannot do long-range Coulomb interaction. Right? So yes, I have this big simulator, but I cannot solve the problem that my other student is doing experiment. So this is a problem, and there are all kinds of very fantastic capabilities being built here. So this is a problem this is a real problem that we have. So the third thing is contact resistance. Okay, so I intentionally use this my contact distance is lower than your contact distance because if some of you were in the recent IBM, you know that there has been some very entertaining and engaging discussion about this. But what we are really fighting, when we do experiments, is okay. I put metal X, you put metal Y. I get this much current, you get that much current. Okay. The problem is, this is not very relevant in my opinion because even if you have a very good contact metal, the VT changes when you get voltage. And so that's not a good transistor. We need some kind of doping. Now, I do not know what does it mean to dope a monolayer. Right? How do you dope a monolayer? Ali Jarvis group at Berkeley is doing very nice work of what they call this charge transfer doping. So they are putting potassium on top of these monolayers, and there is some charge transfer that happens. But it's beautiful for looking into the physics, but it is not very good for actual application because it is not repeatable, and it has a drift problem, meaning it is not bound to anything. So if you keep it like this, slowly and slowly, those potassium ions will go. So you are really talking about again a substitutional doping. And when you think about a substitutional doping, what does it mean? Is it going to then create a lateral heterostructure, or is it actually a doping? It's not clear to us, so we don't know what to do. We can think about intercalation, but we don't know how to predict what to do. Okay, so this is again, you at HKU, you are looking at this doping from the DFT point of view could really help us to actually build up an insight as to what we can try. We need some kind of guideline that okay, try this, try that, and then we can try that kind of stuff. But that's a big problem. The other big problem is usually most of us when we do experiments we have this layer, we put the contact metal right on top. Again, there is this problem. The only interaction between these two layers, according to theory, should be just van der Waals. So should there be a big difference if I put the contact here and contact there? Now, experimentally, we are doing both in my group. I don't see any, appreciable difference. Why is that? What is going on? We don't fully understand. Okay? And again, just doing what we do in terms of LEGF does not help us understand this effect because these are kind of more complicated and problem-specific issues. So what I kind of feel is that being in this situation where we do some computational calculations and some experiments is that for these exploratory devices, the beauty is probably in the trends, meaning we are not really looking for a very quantitative result, but we are looking for some kind of a trend that gives us an insight to do my next experiment and build a coherent understanding. And that's the problem. And so I kind of, in my opinion, I kind of feel that challenges in computational electronics for at least exploratory devices are probably becoming problem specific because each problem is different. We are looking at a different material and each has its own problems. So and one size fits all may not work because we need to go and look at our problems, see what specific problems we have for this material and try to solve them. So as a computational person, we may have to start working in this frame of mind that we have to carefully choose our problem and try to solve those problems very, very carefully and in a very focused way, which then brings to this more generic question that Suman pointed out, is that what is the problem? What is the problem that we should look at as a device physics community? And so I stole this basically quote from Arun. So the quote goes like, the Stone Age did not end because we ran out of stones. So the point is that the Stone Age ended because we found new solutions. to kind of similar problems. And in a very broad sense, the problems, the underlying problems that those guys at Stone Age were trying to solve are still the same today, meaning we are still trying to improve the quality of human life, the overall human experience. And so, as Professor Lundstrom pointed out, that the overarching problem as a device physics community may not be just to look at what is the next switch, but to look at what is a better solution, which will make a real impact in human life. So that's as a community we may start thinking about that. And so I'll leave you with this quote from N to Go, that only the paranoid survive. And the way I interpret this is that we should expect unthinkables to happen. And so probably, it makes some sense to start thinking about things that are seemingly unthinkable. So let me just acknowledge the students. They do all the work, and I come to Hong Kong and give the talk. So that works very well for me, but I should at least acknowledge them, and of course all the sponsors without whom nothing would be done. So thank you very much.
Questions?
So you seem to have, you said graphene is a problem. Well, how do you see, in the physics community, we work like crazy on graphene field. Do you see any, tangible, real application out of this material?
So, I should qualify that carefully. That to me, I think graphene is beautiful for physics because you can see so many things and so many different phenomena. When we look at specifically electronic applications, it is very difficult to see how it can be useful. Even if you go to very so. Digital electronics, Professor Lundstrom has a commentary on it that most people believe that there is no way because there is no band gap. Now people are looking at RF applications, but even if you look at very high frequency, high power RF applications, you need an amplifier gain which he does not have because of the current will not saturate. On the other hand, now you can think about low frequency, low noise amplifiers like Suman actually has worked on that. But even there, the problem is that at the low frequency range, the conventional transistor guys, they know, there is a way you can show that if you go to low dimensional materials, your device becomes more and more linear, which is good for a low frequency linear amplifier kind of application. So from that point of view, graphene is nice. But the conventional transistor designers over many years have figured out many different circuit tricks to actually make their device linear. And so once you start comparing with those, it does not look like that there is enough benefits from there. Now, graphene, of course, is being looked at in other applications, like sensing, like wrapping around things, and like transparent electrodes for solar cells. Those are different because there the whole requirements are so different that maybe there is enough there. But whatever I have looked at is mostly electronics applications, and my personal opinion is probably there is not.
Can I ask one more about these negative capacitance?
Yes.
You did say that you are not inventing energy out of this. But you did save energy because you somehow overall your slope is smaller, but you did not save energy somehow, right? How do you think about this?
So it is something like that. That you see that you are using energy from where it was stored in the lattice of a ferroelectric material. It is actually storing energy. And it is giving up energy and it is storing energy again as you go through that polarization switching. And so if you look at the energy saving we usually in a conventional transistor we will say energy CV squared. So if I go down by X amount in voltage, I save X squared. But here, actually, if you look at it, I'm not saving X squared. I'm actually saving just X. Because the charge is still the same. I'm just reducing the voltage. So Q multiplied by V is going down just by the factor that is going down. And the difference between X squared and X is being given to the circuit. So it is basically the fact that as you change the lattice, distort the lattice of the system, the change in the polarization is actually changing your dielectric capacitance. That is how you are kind of, the energy that otherwise the ferroelectric would have given to the environment, you are kind of absorbing it in your dielectric system. That's how you are kind of saving that much energy.
So a follow-up question about the graphene. Some people are talking about multi-layer graphene. If you add a particular electric field, it may induce a gap.
Right.
And that could, just one way to resolve the problem. In a single layer graphene, there's no gap. It's not a real semiconductor. So you have any comment if that kind of things could be useful?
So again, we looked at it not very extensively, but a little bit. There are two things. A is that electric field, the amount of band opening that we have seen with that is around 300 to 350 millivolt so far. I mean, theoretical calculations probably show that even bigger is possible. But experimentally, there is this person called Feng Wang at Berkeley. He does a lot of photoluminescence experiments. They are showing something around 300 to 350 millivolt. That is also too small because you are going to get extremely large tunnel currents because of that. The other thing is that vertical electric field, often there is this idea that it's a static field, so it does not take any energy. But actually that is not true. So, I mean, you'll have to also bring that into account. I mean, the thing is, if you compare with nanotubes, for example, nanotubes are intrinsically so much better, right? And they have the right band gap, they have the extremely good mobility, they get very good current, but still the benefits are not big enough that they have found their way into the real technology. Graphene to me has even a bigger problem, and you don't even have the band gap. Now you are. So that's, I mean, to me, I see that the differential advantage may not be big enough for
For the photodetector, did you add the external bias for your program?
Sorry.
For photodetector,
yes.
You add an external bias.
We added an external bias. Yes.
So how voltage? Is 10 voltage or?
No, so what we did is for our photodetectors where we are showing the results, it's around 4.7 volts.
Okay. Did you work in the visible light regime? Visible light regime, what's the working frequency for the photodetector?
So we actually looked at different wavelengths. So what we did is RGB.
Okay.
And basically what we compared our results is green light.
Oh, because I also know that some groups also use silicon. It's just silicon absorption, and then they can use the graphene. Also use graphene to a photodetector. If you add for the photodetector, you add a very strong external bias. It's even graphene no band gap is also okay because they just do a channel, right?
Right. Because
the silicon also has a very strong absorption. It just separate the electron hole. It has photodetector. So there's some advantage your photodetector. I remember you achieved a very high turn-off ratio. What's the physical reason?
So the physical reason is we are only comparing it with the large area photodetectors where there is no p-n junction.
Okay.
And MOS2 amorphous silicon creates a p-n junction.
Okay.
And so the charge separation is better.
Why you say it has a p-n junction?
I mean, it is like a p-n junction.
Like p-n junction, but you did not dope, right? Did not dope the silicon.
No.
You adopt silicon?
No.
Intrinsic.
But, yeah, but amorphous silicon is naturally n-doped.
N-doped. So
Yeah.
it's similar to P dot. This is similar to P dot.
Right.
Okay.
So it is almost like an n minus junction. So the
Okay.
main thing is there is a built-in electric field here, which can separate.
Okay.
Yeah. So
Okay.
it is in spirit very close to having silicon and a graphene on top.
All right. I also see some work to a solar cell.
Right. Yeah.
Okay, thank you very much.
Yeah, thank
So,
Thank you very much.
So Professor Zhang will give the